Ms. Geeta Avula. She is a Senior Technical Manager, Dassault Systems, and is responsible for driving initiatives such as electric vehicles, additive manufacturing, cloud solutions to guide companies on the technology. She is engaged with the company for around 2 decades. Ms. Geeta has supported customers in various industry segments on technical support, training, best practices, and methodology setup in the usage of software and working with global team. She is supporting clients in the EV space. She holds a master's degree in computational mechanics of material and structures from University of Stuttgart, Germany. Today, Ms. Geeta will talk about electromobility in India. How can virtual twins help EV value chain? Let's welcome Ms. Geeta.
Yeah, we had interesting discussions from other panelists in terms of how we are evolving in the EV space and the trends and challenges we are facing. And in the next 10 minutes, I put together a short presentation where I would like to take you all through on how virtual twins can help in the development of EVs, right from cell to battery pack to full vehicle. So what are virtual twins? So virtual twins are essentially used to model complex systems. So it could be it either from cars to cities to factories to human hearts, wherein we could simulate the functioning of these systems with a very high level of accuracy. And so be it either assembly or sub-assembly, or it could be even at a system or a subsystem level, we could build a virtual twin that is a replica of the actual physical model on the digital platform and understand the behavior and performance by simulating and doing various testings. Essentially, by avoiding physical costly prototyping, we can directly go from ideation to creation by using these virtual twin techniques. So if you look at the transportation and mobility industry, that is the automotive industry, the other panelists have certainly spoken about the industry challenges, and like the others have said, emission is a concern. And from the automotive industry, we see that the emissions account for about more than 25% of the global CO2 emissions. And in order to also achieve the global greenhouse gas reduction targets, everybody is moving towards zero emission and autonomous vehicles. And typically we see that OEMs are using hundreds of test vehicles per model every year, for testing purposes and other things. So clearly the use of virtual twins will help advancing in the advancement of prototyping and physical testing. It will help in the shortening of overall time to market of new vehicles, reduction in costly vehicle recalls, that is the warranty cost can be avoided, wherein we can understand the system performance by virtually simulating and understanding the behavior of the system, and thereby reducing the overall costs of the vehicle and the systems or the other components. So if you look at electrification, of course, it uses renewable energy, it is clean, efficient, quiet, but then certainly it comes with certain market challenges as well, which is they are expensive, at least at this point of time, and range is of a concern, and charging time is also a concern, which these things are being looked at, but as of today, these are some of the challenges that we have when we talk about electric vehicles. And if you look at the trends in electric vehicles, obviously everybody is striving to have better performance than ICE vehicles, trying to provide these vehicles at an attractive cost, and range is a huge factor when we talk about EVs, and everybody is striving to have better battery life, reduced charging times, and yes, in EVs we are talking about batteries mainly of lithium ion, and safety is of concern, so safety and durability aspects are also being looked at. So if we talk about electrification, we typically have three key domains coming to our mind, which is battery, e-drive, power electronics, and then we look at the integration of these three domains at a full vehicle level. I'll speak a little bit about each of these three key domains and explain in terms of how our solutions can help in understanding these domains better. So if you talk about batteries, we have a complete digital twin coverage right from chemistry to systems. So what you're seeing on the bottom left-hand side is the molecular and atomic behavior, which is in a 3D level, where we have solutions coming in from our sister brand called Biovia, pitching in, which would help users understand, let's say, the anode, cathode, electrolyte, SEI characteristics, and so on. And then we move to the 1D level modeling, where we could, model the cells, module, or pack at a 1D scale, and understand, let's say, the charging aspects, the aging aspects, we can study the thermal characteristics, understand the electrical behavior, thermal electrical behavior, and so on. And we could go one level deeper and then look at the complete 3D level design and simulation, wherein we can model the cells in a more detailed manner, and also modules and pack, and look at the mechanical, thermal, diffusion aspects, and so on. And then, of course, look at full vehicle integration aspects as well. So if you see this particular slide, so we have solutions covering right from the battery materials and going all the way up to cell, module, pack, and then a full vehicle. And talking about battery cell, there are a bunch of workflows that people typically look at. That is, one can start off with a detailed battery cell design, and then look at performing MDO kind of studies. And we could look at electrochemical performance, look at thermal electrical losses, that is trying to understand where a cell is getting charged and discharged, different charging and discharging cycles, what are the thermal electrical losses. We could look at stiffness, durability aspects, the safety aspects can be simulated. That is the thermal runaway, abusive conditions like short circuit, all of that can be simulated. We could look at degradation, aging aspects, and so on. And moving to module and pack, the same level of workflows are applicable, except that here we are talking of a much larger model. So typically in a module, if you're considering, let's say, cylindrical cells, you would have somewhere between 300 to 400 cells, and in a pack you would have somewhere between the 13 to 14 such modules if you are talking about a four-wheeler. Again, thermal management studies become quite critical when we are talking about module and pack level simulations. And here again, we could look at strength, stiffness, and durability aspects, the safety aspects, that is, what happens when the battery pack is dropped, or there is something like a nail penetration which kind of occurs, and so on. So we could also look at cooling aspects, that is, which type of cooling is going to be efficient for your battery pack system, and so on. So moving on to the next domain, which is electric drive. So it's almost like an ideal unit, which has mainly three components. You have the electric machine, gearbox, both of which are encapsulated in a structural housing. So it's typically a high energy density machine which is rotating at a very high RPM. And when you have something rotating at such a high speed, of course, there are frictional issues which has to be mitigated, which means that there needs to be proper lubrication in place, and so on. And also, the electric machine and the gearbox are encapsulated in the housing, which would act as the speaker itself. So you have to work on mitigating the noise aspects as well, and of course, look at light weighting and things like that. So in order to help the users understand the behavior of the system better, so once we have come up with something called as electric drive industry process, where once the system design is in place and the verification and the validation is done and a concept design is built, and from there, a detailed design takes place. To understand the performance and behavior of this detailed design system, we have some standardized workflows. Like, let's say, we could look at the noise and vibration aspects. We could look at the electromagnetic performance. We could look at thermal management, lubrication studies, strength, stiffness, and so on. So we have guided workflows for each of these aspects, which would help users, understand as to what are the steps which needs to be followed to carry out these analysis. And of course, these are clubbed with the other domains like battery engineering and power electronics. So I would like to play a very quick video showcasing some of these solutions. So I'll allow you to watch it for a minute. So with that, let me move to the last domain, which is our power electronics. So when we say a battery is the heart of an EV, power electronics is like the brain of an EV controlling, different units. So if you look at the functional components of power electronics, we have, DC-AC inverter, DC-DC converter, we have the plug-in charging systems and the wireless charging system. So typically the challenges we see with this unit are mainly again on the thermal management. EMC compliance is again one key thing when we talk about power electronics, and of course space and weight reduction aspects are there with any domain we talk about. So if you take a look at this what we call a three-phase inverter power module, and so we have different components, like you have IGBTs, diodes, then you have the wire bonds connecting. When the DC to AC, conversion happens, there is a lot of switching that happens, which generates a lot of heat, and this has to be mitigated with proper, system with the proper cooling system in place. So using the solutions, we can, understand as to how the heat is getting conducted through the base plate, through the cooling fins, and come up with a good cooling system in place, which would address this thermal management issues. So we could perform what if kind of design scenarios and understand what would be the best cooling system in place, which would help mitigate these issues. And we have seen the solutions for different domains. And if you look at full vehicle integration, so we could look at the vehicle dynamic aspects to characterize rider handling, and we could look at studies like crashworthiness to understand the impact studies. We could look at full vehicle thermal management, what we call as sun soak simulations. So let's say typically you have the vehicle under the sun for about, say, 7 to 8 hours, and you want to understand the impact of how the temperature is being absorbed in the cabin, and how to have a better understanding of the battery positioning for better thermal management. So all of these studies can be done at a full vehicle level as well. And just a quick glimpse of how our solutions are being used across the world. So most of the startup companies and OEMs are using our digital twin solutions for their EV development. And be it either a concept car or an SUV or a truck, there are quite a few companies across the globe who are using our solutions. And that was a very quick overview. I know there is a lot of content. So a couple of links where you can find a lot more information on what I've just covered, and you could always reach out to us if you have more questions. And with that, I would like to conclude my talk.